And so we will start with the second talk now by Joé Brendel from Université de Neuchâte, who will talk to us about real Lagrangian Tori in Toric symplectic manifolds.
Yes, thank you very much, and thank you very much to the organizers. So, as the title indicates, we'll be talking about real Lagrangians, more specifically about real Lagrangian Tori in the context of toric symplectic manifolds. And just to start, I'd like to recall first what real Lagrangians are. So I fix a symplectic manifold M omega, and on this symplectic manifold, I choose an involution which reverses the symplectic form. So by involution, I mean it squares to the identity. And by reversing omega, I mean the pullback goes to minus itself. And these objects have the nice property that if you look at fixed point sets, then whenever the fixed point set is non-empty, then you'll get automatically Lagrangian. And so these are the objects that we are interested in. We'll look at Lagrangians which arise as such fixed point sets. Right. And so this has the nice property of being invariant on the symplectomorphisms. So if you have such a real Lagrangian and you map it to another Lagrangian by symplectomorphism, what you get will again be a real Lagrangian just by conjugating the anti-symplectic involution. This turns out to be very useful in many contexts. And so the main question that we'll be addressing is, given a Lagrangian, can we say something about if it's real or not? And we'll address this question in mainly for Lagrangians in toric manifolds. First of all, for toric fibers, and then for exotic tori also. So for Shekhanov tori in particular. But before going to the toric context, I'd like to give some general examples, maybe to give just a flavor of what real Lagrangians look like. And the easiest one is, of course, in Cn, where you just take Rn. This is where the name real comes from, because in the context of complex algebraic geometry, you think about complex conjugation as your involution. So in this case, Rn will be the fixed point set. And a non-example are product tori in Cn. In the case of n equals 1, you can see this by hand somehow, because you will just get the circle and the plane. But then if you want to fix the circle and the plane, you would have to exchange somehow the bounded interior component and the unbounded exterior component. So this is obviously not possible. I mean, even on a topological level. So you don't even have to go to anti-symplectic involutions, but even for involutions, this will not work. Second main example maybe is the zero section in cotangent bundles, which is quite obviously real because you can invert the momenta. So you just map QP to Q minus P, and this will fix the zero section. And in the same way, you can actually show that like sections of closed one forms, for example, are also real, because by the conjugation argument basically that I gave before, because you can map the zero section to them by symplectomorphisms. And another classical example is inside of CPN, equipped with Fubini-Studi form, is real projective space. And here you just take complex conjugation on non-homogeneous coordinates, and this will fix RPN. And this actually generalizes to all toric manifolds, which gives rise to real, so-called real toric varieties. Right. Maybe the most important one of the basic examples for us today is will be S2 equipped with the standard area form, and I'll be looking more specifically at circles of constant height. So I indicated here that we have some kind of height function, maybe the usual one where you embed S2 into R3 and then you look at just the Z coordinate. And then you can see that if you ask which one of these circles is real, that there's basically only one among them, namely the equator. And the other ones cannot be real because you have a problem with areas, right? If I take, for example, the upper circle here, I would have to map the upper disk to the lower one, but they have different areas, so this doesn't work out. Which is already quite interesting because smoothly it works. So smoothly you could of course do this, but once you have the anti-symplectic condition, then this breaks down basically. And this is a special case of a more general remark, which is also quite useful. Namely, if your ambient manifold is monotone and L is real, then L has to be monotone as well. It's not hard to show, but this is quite useful because this gives you first obstruction. It tells you that you only need to look at basically only your monotone Lagrangians are candidates for being real, and if your ambient space is monotone. And so the next step will be to kind of generalize this example, if you wish, because I will move to the toric context now. And so we've already talked about, I mean, Morgan has already talked about toric manifolds, so maybe I will not introduce them in detail. But let me just give you a picture. So you always have, in the toric context, you always have a moment map which maps the manifold to a Delsand polytope, as I've indicated here. And then over the interior of the moment polytope, if you take pre-images, you get Lagrangian Tori, and this is what I will call toric fibres, and those will be the first Lagrangians we'll deal with basically for this question of being real or not. Okay, so there is one more technical assumption that I'll make on the on the moment polytope. It's a kind of a combinatorial assumption, if you like, and I call it property Fs. F standing for facets and S standing for symmetry or symmetric point. And I basically want that every facet of the moment polytope contains a lattice point. So you have, if you want, you have Zn sitting as a lattice inside of Rn, and you want a lattice point inside of each of the facets such that it's minus this lattice point is also contained in the moment polytope. And actually would like to get rid of this property at some point because conjecturally this is already implied by M being monotone. But unfortunately the conjecture has only been checked up to dimension 9. So for now, if we want to make general statements in arbitrary dimensions, we'll have to include this as an assumption, basically. So maybe later on, I'll make some remarks in the proof, and then you'll see how this strange property enters into the proof. Right. So now let's look at some examples. So here you see the moment polytopes of all monotone examples in dimension 4 of toric manifolds. So you have S2 cross S2, and then you have monotone blow-ups of CP2. And so now we wonder which ones. So over every one of these shaded points here in the interior of the moment polytopes, you have a toric fiber sitting there, and we wonder which ones of them are real. But just by the monotonicity remark that I made before, because all of these spaces are of course monotone, you can exclude already all of them except for the central fiber, because the central fiber is the only toric fiber that is monotone also. And so the question basically becomes, well, which one of these 5 monotone central fibers, so when I say central fiber, I mean the monotone fiber, the unique monotone fiber, which one of these central fibers is real? And I guess one of the examples we can figure out by hand, namely the S2 cross S2 one, because what we have here over the central point is just the Clifford torus, which is the equator times the equator. So if you go back to the example that I made before about S2, you can see that in the factors they are real. So you can just take the product of the two anti-symplectic involutions on the factors, and so you can check that this one is indeed real. So in S2 cross S2, the answer is yes, the central fiber is real. And for the other ones, let me first make a remark about smooth topology somehow, because actually there is already an obstruction coming from smooth topology, which is classical theorem by Smith, and it tells you that if you want a set to arise as a fixed point set of a smooth involution, then you have certain conditions which have to be satisfied, namely the Euler characteristic of the fixed point set and the ambient manifold has to agree mod 2, and the dimension of the total homology of the fixed point set has to be bounded by the dimension of the total dimension of the homology of the ambient space. So this somehow says something like that the fixed point set cannot be more complex somehow in a topological sense than the ambient space. And this is interesting and relevant for us because it already excludes some of the cases. You cannot even have tori as fixed point sets of smooth involutions. So for sure you cannot have them as real tori inside of CP2 and CP2 twice blown up. And for example, here you can apply the first Smith equality. And so if I go back to my examples, we can exclude this one, B and D, basically by topological means already. And then for the other two, we need the following theorem, which is one of the main theorems that I'd like to discuss today. So if the central fiber is real, then the moment polytope has to be centrally symmetric, meaning that if I apply minus the identity to it, it has to be invariant on the minus the identity. And actually the converse is also true, but it's a little easier because it's on the construction side, right? It's not on the obstruction side. So you can just basically lift in a way the minus identity map on the moment polytope to the total space of your fibration. And this is joint work with Juntae Kim and Jian Moon in another project. And so this theorem basically completely answers our question about the central fibers. So sorry for switching a lot, but because it says that here we can exclude B, C, and D. Well, two of them were already excluded, but okay. And but A and E, actually here the central fiber is real. So also in the threefold blow up, you have also a real central fiber, because this one, you can just see it. It's centrally symmetric. If you apply minus the identity, then it gets mapped to itself. All right. So just a few words about exotic tori. So the first result in that direction goes back to Junte Kim from last year, and he showed that the Shekhanov torus in S2 cross S2 is not real. Of course, you might wonder about why this is looked at in S2 cross S2. Same question can be asked could be asked in C2, because this is the first space where the Shekhanov torus was constructed. But actually, it's already by the same criterion that by the same smooth criterion, it's already excluded in C2, because you don't have enough topology to have a real torus there in C2. So you embed it in S2 cross S2 and you ask the question there. And so it turns out that it's not real. There's actually a much stronger result and more recent result by Kim, stating that the Clifford torus is unique as a real Lagrangian inside of as a real Lagrangian torus inside of S2 cross S2, which is quite interesting, because as you may know, there are infinitely many monotone tori in that space, which was shown by Viana, and this shows that there's some discrepancy between monotonicity and realness. Okay, and so the second main result today is basically a generalization of Kim's first theorem. Namely, I did the same thing, but in general, in the general monotone toric case. So can show that there's a Shekhanov torus sitting inside of every one of these spaces. And you can show that Shekhanov torus is exotic, first of all. You have to show this. I mean, it's not obvious. You could end up with something which is Hamiltonian isotopic to the central fiber, but actually one can show that this is not the case. So every one of them is exotic, and none of them are real. So this is quite different from the case of the central fiber, where it depends really on the toric manifolds you look at. So another maybe interesting remark is that this is a symplectic phenomenon, at least in some of the cases, because you can show that in some of the cases the Shekhanov tori are fixed point set of smooth involutions. So this theorem here is, at least in some cases, you cannot see it by like topological invariance in a way, because topologically speaking, they are fixed point sets of involutions. But if you want them to be, if you want your involutions to be anti-symplectic as well, then it doesn't work anymore for Shekhanov tori. Great. Now maybe I'd like to say some words about the proof, because so one more remark maybe. So the result of Kim is shown by completely different methods actually than the methods that I used, because he uses J-holomorphic disks, and I use the method of first deformations, and I would like to explain to some extent how this works. So this method goes back to Shekhanov in '96 and was used later on by Shekhanov-Schlenk in order to distinguish tori, basically. And one more thing about the proof is that it is, in a way, quite elementary, because the hardest result that you need in the sense of symplectic topology is the displacement energy of product tori in Cn, which is quite a classical thing. And so let me explain how it works. First of all, the first step is to determine the the displacement energy of toric fibers for our toric manifolds. And to get an upper bound on the displacement energy, I use probes basically, so Busa-McDuff's method by probes. And this is where this property Fs that I talked about comes in, because it is used actually to show that all of the points are probe accessible, which is not always guaranteed. This is where it comes in. And the lower bound is actually proved by symplectic reduction. And what you get is the following. Here are some pictures that go along with it. Basically, the displacement energy of a given torus depends on the affine distance of, so this is the affine distance, not Euclidean distance, from basically the base point that you choose to the boundary of your moment polytope. So what I've indicated here are basically level sets if you view this thing as a function of x. So you have on every one of these triangles, you have constant displacement energy. And right, so you see that these are just rescalings basically of the shape of your moment polytope that you have. So this is the first step, and the second step is really going into versal deformations. And let me give you the picture right away. So the idea is not only to look at the displacement energy of the fiber that you're interested in, so in this case the central fiber, but also extend this to some, let's say, some neighborhood U, and this will give you a function which goes from this neighborhood U to R union infinity, just measuring if I shift the base point around a little, how will my my displacement energy vary? And so these things have nice properties, namely some invariance properties on the Hamiltonian diffeomorphisms. This is why they were looked at by Shekhanov and Schlenk. But today we are interested in them in another sense. Namely, remember that we want to say something about real Lagrangians, but for now I've just talked about displacement energies. So, but the link between the two comes from the following lemma. So if your L is supposed to be real, then you have some kind of symmetry condition on this function. Namely, if you precompose it with minus the identity, it has to be left invariant. And this basically comes from the fact, so if I go back here, comes from the fact that antisymplectic involutions preserve displacement energy. So if I go back here, if I have, yeah, I'm finishing up, I'll be done in 30 seconds. So if I go here to, if I take my antisymplectic involution, this point in a certain normal form of the antisymplectic involution gets mapped to its antipodal point. So what happens is that the tori come in pairs which have to have the same displacement energy. And this gives you basically this condition that you have to have this symmetry of reflecting with respect to the origin, with respect to what I showed before, these level sets of the functions. Okay, and since I'm running out of time, let me just say that somehow the same method works for exotic tori, because in their neighborhood, in their vicinity, you somehow always have toric fibers. I'm going to stop there. So thank you very much.
So thanks very much, Joé. So are there any questions? Please don't hesitate. You can just unmute yourself and ask. We have a little time for questions if you have. Let me see, there are things on chat. well, so I had a little question, Joé. So it's about this result of Kim you mentioned. So what was, so compared to this vessel deformation or, deformation method, so what was the difference with his approach? You said that they are using holomorphic curves.
Yes, so what Kim does is basically, he does a count of Maslov two disks, and he shows that that essentially the disks have to come in pairs, so you have to have an even number of Maslov two disks, because, well, you can basically see this because the Lagrangian, if you have a disk on your Lagrangian and you use the anti-symplectic involution, you have to get another disk on the other side, basically, of the Lagrangian. So, of course, there's some technical things to do.
Right. Yeah.
This is essentially the argument that the count of Maslov two disks has to be even. But for the Shekhanov torus in S2 cross S2, it's equal to 5. So this is done by Shekhanov-Schlenk. And so,
sure, and the fact that the number is even, so the only difficulty I would imagine is regularity, right? Because no, I mean, to see that you have no fixed points, maybe that.
Yeah, I think so. Yeah.